It's my pleasure to introduce Mr. Shiroman Prakash. Mr. Shiroman Prakash is pursuing a PhD in theoretical physics at the Tata Institute of Fundamental Research, focusing on string theory. He has a bachelor's degree in physics from Johns Hopkins University, where he received Provost Award for undergraduate research, a master's degree in physics from the Indian Institute of Technology, Kanpur, where he received awards for Best Academic Performance and Best Project Work. He attended CONSAS 2008 and 2009 and is a regular visitor to the Dalbagh Educational Institute, where he occasionally gives mini lecture courses on various topics related to string theory. I welcome Mr. Shiroman Prakash for his tutorial.
Alright, so first let me just thank the organizers for inviting me again, and as you said, time at CONSAS. Again, I'm never sure exactly what to say in a talk, in an introduction to string theory at a conference focusing on quantum and nano-systems. So since I don't know what to do, I just give something to do each time. Is just a general introduction to string theory with a view towards just creating a qualitative appreciation for the mysteries of quantum physics. And no explicit attempts we made really to connect the quantum and nano-systems, but we'll see what. Right, so this talk, I said, will provide a qualitative introduction to string theory, which is a candidate for a unified theory, describes gravity and other forces, starting from quantum mechanics. And an important point is that string theory is experimentally untested and, barring any unexpected, will remain untested in the near future. And this is not a problem with string theory so much as just the general idea of quantum gravity is difficult to test. But even if we don't know whether it's the quantum theory of gravity describing nature, it's at the very least a concrete toy model for a quantum theory of gravity and unified quantum theory, and as such represents a current to understand life nature using quantum physics. So, to interest you in it further. So this is the outline of talk. We'll start with quantum physics, go on to gravity, string theory, and M-theories, dualities, and applications. Again, I'll tell you that the talk will be very live in its philosophies, but I think that's more interesting. Okay. Quantum physics. So let's open with a quote: "When you come to a fork in the road, take it." So this is Yogi Bharat teaching us, was obviously referring to the two-slit experiment when he said this quote. And it's not my idea to use this quote. This is the guy, Mr Shankar at Yale, used this when challenged to explain quantum mechanics to humanities professors, and he used it. I thought it's a good idea, so use it. And okay, this is a two-slit experiment, which hopefully you're familiar with. If not, I suggest you look at the Feynman lectures on physics. But very briefly, an electron starts at A, and to calculate the probability we later observe it at B, we assign a phase to the two paths connecting A to B. We then add these two phases, which may interfere constructively or destructively, and then take the absolute value of the result to obtain the relative probability the electrons observed at B. Okay, so we can try to generalize this experiment in a perhaps obvious or non-obvious way by adding another screen with three more slits. Okay, in this case, you have to sum over 6 paths to obtain the probability the electron is seen at point B. Again, this example comes from this book. Okay, so adding a screen with more slits requires to increase the number of paths we have to sum over. Now we can further generalize it by adding another screen with a large number of slits. So if we add a screen with an infinite number of slits, it's as good as having not even added a screen at all. And we could, in principle, add an infinite number of screens, each with an infinite number of slits. And that's as good as having no screens or slits at all in the first place, but now we see that we have to actually sum over an infinite number of paths, even when there's no screens or slits in the first place. So this is basically the rigorous definition of the path integral formulation of quantum physics, which is that if an electron is, say, at A and we want to observe the probability it's seen at B, we associate a path, a phase with each possible path that the electron could in principle have followed, and we have to add all those phases up, which add and interfere to give the probability amplitude for the electron to go from A to B. Or to be more precise, we can see the following quote. So Dick Dyson. So Dick Feynman told me about his sum over history's version of quantum mechanics. So the electron does anything it likes. He said it goes in any direction, at any speed, forward or backward in time, however it likes. And then you add up the amplitudes and it gives you the wave function. And I said to him, "You're crazy," but he wasn't. Okay, so now what has been the big successes of the path integral formulation of quantum mechanics? Well, the most successful theory and the theory which Feynman helped to discover is quantum electrodynamics. So again, we sum over paths. Quantum electrodynamics is the theory of electrons, positrons, and photons, and how do we do calculations in quantum electrodynamics? So then we sum over all possible paths these electrons, positrons, and photons take, but we introduce an interaction vertex which allows electrons and positrons to emit and absorb photons in sum over paths. And for each interaction vertex in a path, its contribution to the sum is weighted by a numerical factor proportional to the charge of the electron. So, for example, using diagrams like the one shown, we can calculate the electron's enormous magnetic moment, which happens to be one of the most accurately predicted and measured quantities in the history of science. But a QED is not the final quantum field theory despite all its successes. So we can imagine colliding electrons together with higher and higher energies. Well, not really have to imagine, we've done it, and what we find is that QED no longer is an effective description, and we have to, and for experiments carried out at higher energies, we have to introduce new particles and eventually new forces to describe the experimental results. And this is pictured in this conceptual diagram. We start with quantum electrodynamics, which is valid at low energies, but if we do experiments at higher energies, we find that we have to use a theory which has an additional particle which is massive called the muon, but that theory at low energies would reduce to just pure QED because the muon is heavy, and at higher energies we introduce muons in taus. Still higher energies we have to introduce a new force altogether. We find that the electroweak force, electromagnetic force is actually part of a larger force called the electroweak force, and if we could do experiments at even higher energies, we might find supersymmetry or gradient phi theory. And again, this example illustrates the idea of a. So say we think of the standard model as microscopic theory, or microscopic or ultraviolet theory, UV. However, the point is, if we probe the theory with probes with low energy or long wavelength probes, it effectively looks like a different theory, for example QED. And okay, in general, a high energy UV theory contains all information about the low energy IR effective theory, but of course a given IR theory may be the infrared limit of many different theories. So the principle derived IR theory from the more fundamental UV theory is possible, but it's often highly non-trivial or impossible in practice. For example, we can't predict the mass of the proton starting from QCD just because we don't know how to start calculation. Okay, so that represents our current, a brief representation of our current understanding of quantum field theory, and of course the ideas of effective field theory and quantum field theory extend beyond high energy particle physics. They're relevant for the collective behavior of many electrons and metals, and quantum field theory is in general a theory of nearly everything that's an important framework for describing results in all sorts of areas of physics. But now the question is, what are the implications of quantum mechanics for gravity, or vice versa? So just very briefly, Einstein's general relativity tells us that gravity is the dynamically evolving shape of space and time, and the two standard features are that space-time is expanding and originated in a Big Bang, and more importantly, if enough energy is placed in a small enough volume, a black hole forms, which is, as we all know, one-way event, one-way surface in space and time from which nothing can emerge. So say we want to probe physics or the geometry of space-time at smaller and smaller length scales. So the uncertainty principle tells us we must collide electrons together with higher and higher energies. As we see, so we want to get the bigger and bigger map of the theories in the diagram. But the problem is, when we take gravitational interactions into account, if we place enough energy in a small enough region, we'll actually form a black hole, and then we can't really see what happens inside. So this suggests the existence of a minimum length scale we can probe, which is called the Planck length, and comes out to be, say, at least 10 to the minus 33 centimeters. Okay, so why is quantum gravity difficult? In other words, you can say that the sum over parts when we include gravitational interactions becomes ill-defined, or at least ambiguous beyond the leading approximation if we try to include gravity. And the correct interpretation is that new physics must exist before we reach the Planck length. And just such phenomena have been encountered in physics before, and just to give a review of where it happened earlier. Say, for example, you ask the question, what is the charge of an electron? So the charge you observe at large distances from the electron is screened by a cloud of virtual electron-positron pairs popping in and out of existence. Hence, it's smaller than where the charge would be if we viewed it from a closer distance. So we can ask, how does the charge of the electron change as we observe it from closer and closer distances, or at higher and higher energies? Okay, and QED predicts that the observed charge of the electron keeps increasing until it actually flips, even while we're at a finite distance away from the electron. So the point is, and such a thing seems unphysical. So just have the electron we see is an electron screened by virtual electron-positron pairs popping in and out of existence, like the pi screening. But so you imagine that the actual charge of the electron is larger. But if you calculate what it would be, you'll find that it actually is infinite, even if you're looking at it from a finite distance away. So this is This is called a Landau Pole, which is the distance at which, when you look at the charged electron, it becomes infinite. And the physical interpretation is really that QED doesn't make sense at a fundamental theory, only as an effective theory, and new physics must exist at small length scales before you actually reach the point where the electron charge looks infinite. And of course, in the real world, QED is replaced by the electroweak theory. So indeed, new physics does rise, and you see that Landau pole doesn't exist. So the situation in gravity is similar, but the infinities are perhaps more severe. So then the conclusion for gravity is that new physics has to take place at or before the Planck length. So what are the candidates for such new physics? So one candidate is string theory. And while modeling some experimental results in nuclear physics, physicists considered the quantum mechanics of relativistic strings. And a consistent quantum mechanical treatment of relativistic strings is rather delicate, but after some confusion, it turns out that it does provide a realistic candidate for new physics that occurs at or before the Planck length. So just to summarize briefly, so a particle trajectory traces a one-dimensional world line in space-time, and a trajectory of a string in space-time traces out a two-dimensional surface called the world sheet. The quantum mechanics of string is just a sum over world sheets. Or more generally, we define a quantum field theory living on the surface of the 2D world sheet. And the fields include the location of the string in space-time, so each coordinate is a field, plus you have some additional internal degrees of freedom. And as we know, the sum over world sheets is not consistent in 4 space-time dimensions, and in fact, quantum mechanical consistency for the sum over world sheets to be consistent fixes the number of degrees of freedom on the world sheet, which is, in the most natural interpretation, means that strings must live in exactly 10 space-time dimensions, which is the first, well-known and strange prediction of string theory. But okay, we only see 4 dimensions, so how can string theory be right? But the idea is the standard idea that if the extra dimensions are compact with a small enough radius, then they wouldn't be visible to large wavelength probes, and that's the only possibility for how we can reconcile the 10 dimensions with the 4 dimensions we observe. And it turns out exactly how the extra dimensions are compactified affects the particles and interactions we see in the remaining 4 dimensions. And physical arguments suggest beautiful geometric constraints on the allowed shape of compact extra dimensions. Okay, so how do we describe interactions between strings? So in the case of interacting particles, we introduced an interaction vertex that allowed particles to merge and separate in the sum over paths. In string theory, we just do the same thing. We allow the strings to merge and separate in the sum over world sheets. However, the big difference is that in string theory, the theory describing free strings uniquely determines the interacting theory, because as you see, any point on the diagram looks locally like just a free string. And it turns out that the theory must include gravity, which is in contradiction to particle physics, where you could choose what interactions to add, but you're unable to model gravity consistently. So the question you might ask is, okay, so we have this sum over world sheets that I'm claiming as a quantum, provides a quantum theory of gravity, but how is it really that string theory addresses the problem of quantum gravity that occur at the Planck length? Okay, and in part the answer is just the subtle mathematical miracles that occur in the detailed physical calculations. and other things like supersymmetry, which I can't describe. But the main qualitative feature of string theory is that it introduces a new length scale in physics called the string length. So this idea, and as we discussed earlier, to probe smaller and smaller distances, we need more and more energetic probes. But strings are loops of energy, if you will, and as you put more energy into a string, it tends to get longer. So this introduces a new length scale in the theory called the string length, which you can think as a scale you can probe using strings, up to some caveat. And the fact that the string length is a minimum length manifests itself in strange ways. So imagine one of the extra dimensions of space-time is a circle of radius r. Then you can picture a string moving around the circle with some quantized momentum, or it could be wound around the circle several times. The energy of a string wound around the circle is proportional to the number of times it's wound times the radius, because the energy of the string is proportional to its length, and of a static string, and the energy of the moving string around the circle is proportional to the momentum quantum number divided by the radius. So the result is that if we make the transformation which interchanges where the radius of the extra dimension in units of the string length goes to 1 over r, and simultaneously we interchange the quantum numbers describing winding number and momentum, what we find is we get a different string theory. So it's your choice whether you want to say a string is moving around an extra dimension with some units of momentum, say a small extra dimension with some units of momentum, or whether it's wrapped around a big extra dimension with the same units of winding. So the way to interpret this is that string theory on a circle with radius less than the string length is equivalent to another string theory on a circle with radius greater than the string length. So if you keep shrinking the circle down to the string length, you can't shrink it any further, because as soon as you do, a new description takes over where string length is where the radius of the circle is actually larger than the string length. Okay, and since the string length is the minimum length scale you can probe, if you're lucky enough that the string length is much larger than the Planck length, you simply never reach the scale where the problems of quantum gravity arise. So that's nice, but it might sound like cheating. But the key advantage is that, okay, starting from the limit where the string length is much larger than the Planck length, we can systematically calculate corrections to probability amplitudes as a power series in L Planck divided by L string, which we call the string coupling constant G. So the sum over world sheets, which I described earlier, is really a power series in L Planck divided by L string. And calculating physical quantities in an asymptotic power series which doesn't even converge is generally the best we can do, even in the most successful quantum field theories, because that's exactly what we do in quantum electrodynamics. We have a power series which we know it doesn't converge, but it still works at small values of coupling. So similarly, in string theory, we have a power series which may or may not converge, but it's as good as the power series we have in quantum field theory. So in this sense, string theory is a perturbative theory of quantum gravity. You might ask, okay, I mean that's nice, but the mysteries of quantum gravity are that at the Planck length, space and time break down, and all sorts of strange things happen, and does even the notion of quantum mechanics make sense? So what can string theory tell us something about what happens when actually L Planck is comparable to L string or greater than L string? So if the string length becomes equal to the Planck length, the power stays unequivocal and we don't really know what happens. But indirect arguments have revealed that we can say something about if we go even further and if we go to a limit where L Planck over L string is actually very large. So if the string length is much smaller than the Planck length, remarkably actually string theory makes statements about what happens there. So before we go to that, recall that there are 5 string theories and these are their names, which aren't important, but the point is T duality, which we discussed earlier, is a classical duality which relates some of these string theories together. So we see that there's, in addition to these classical dualities, there exist quantum dualities which relate the string theories between weak and strong coupling. So if we exchange the Planck length with the string length, what happens? It turns out that, for example, type 1 string theory becomes SO32 heterotic string theory, which is a different string theory. So this means that okay, if you make the string length much larger than the Planck length or much smaller than the Planck length, you can calculate physical quantities. So in one regime, quantum gravity is really weak. In the other regime, you would say quantum gravity looks like it should be extremely strong, but actually there's another description where quantum gravity again is weak. And you just trade L Planck for L string. And so we can calculate quantities where L Planck over L string is very small or very large, but in each case we have to use a different string. So one theory takes over the description of another theory. The same thing happens with type 2b string theory, except for that it's dual to itself. So if you try to make the string length smaller than the Planck length, they just interchange roles and you're back with type 2b string. Okay, but in the remaining 2 string theories, actually something different happens. So if, say, you manage to probe length scales smaller than the Planck length, and the other 2 string theories, namely type 2a string theory or heterotic E8 cross E8, you'll find that a previously hidden, the conclusion based on consistency is that a previously hidden extra dimension would become visible, and for sufficiently large values of the coupling constant, a new theory called 11-dimensional supergravity emerges as an effective classical description of physics. And just a word about 11D supergravity, it's a unique supersymmetric theory of gravity. And we don't know how to quantize 11-dimensional supergravity, but it's conjectured that an unknown theory of 11-dimensional supergravity exists, which we call an M theory. Okay, so anyway, putting all these dualities together, we can see that all the string theories are related to one another and also to this 11-dimensional theory, and there are different, limiting cases of a single unknown quantum theory dubbed as M theory. And the M theory contains 2D membranes instead of strings, and once even called membrane theory, but we can't carry out sum over membrane trajectories. Some physicists describe use that acronym M on your name. Okay, so ultimately M theory in its full 11-dimensional form is an intrinsically quantum theory of gravity that doesn't contain strings, so we can't say much about it. But okay, what is this brief excursion in Planck length physics? Has it really taught us anything or helped us in our understanding of quantum physics? And the answer is it has. And the point is quantum field theories without gravity, such as QCD, play a crucial role in our understanding of physical systems. So just as M theory had many classical limits which were often non-trivial, and one classical limit looks like a highly non-trivial interacting quantum regime from the point of view of a different classical limit. So the point is, since we know a given quantum theory can have many classical descriptions, is it possible to find new, effectively classical dual descriptions of strongly interacting quantum field theories that already exist in nature, analogous to the ones we found in string theory? And the answer appears to be yes, though not necessarily for there's much work needs to be done, and many examples of dualities applicable to a variety of quantum field theories have been discovered in the context of string theory. So in fact, the quantum field, the most important duality is one which says that the quantum field theory may secretly be dual to a theory of quantum gravity in one higher dimension. So recall that quantum field theories look different when probed at different energy scales. So what the key idea is that we can interpret the energy scale of the probe we use to observe the theory as actually a new spatial dimension. And if we do this, a 4D QFT is formally rewritten as a 5-dimensional theory, which in some cases may actually be a quantum theory of gravity. And if you go and limit where this quantum theory of gravity is classical, that corresponds to a new strongly interacting limit of the original QFT, which we previously, in a regime where we previously couldn't do any calculation. So, much work is on to this is just a picture of it. So the ultraviolet quantum field theory exists at the boundary of space-time, and then its low energy excitations are projected into the bulk. So this is like quantum field theory with the energy scales as an extra dimension, and this is a rendition of anti-de Sitter space, which is just one geometric shape. The geometric shape that a quantum theory of gravity would have if it's dual to a conformal field theory. Alright. So just to conclude, okay, in his recent article, Stephen Hawking and Leonard Lorimer write, M theory is not a theory in this sense, but a network of theories, and it's a bit like a map. To faithfully represent the entire Earth on a flat surface, one has to use a collection of maps, each of which covers a limited region. And I tried to convey that to you that this collection of maps analogy is underlined by the notion of quantum dualities, and hopefully in the future, dualities discovered in the context of M theory could eventually be used to solve problems in non-gravitational real-world quantum systems. Hopefully.
We probably can have one question, one or two.
Well, it's enough energy. I mean, to probe small length scales, you need to use high energies according to the uncertainty principle. And to probe a length scale as small as the Planck length would require enough energy to create a black hole. So you throw in your probes with that much energy, but then all that happens is you create a black hole and you can't see what's inside. At least that's in classical gravity. In the quantum theory of gravity, maybe you can probe length scales smaller than the black hole, and that's not so clear. But also, okay, these dualities illustrate that the Planck length really, you try to probe it and you can't do it because a new description emerges. Is that clear?
Thank you.